Okay, so we're going to look at an important example, another important example of a vector field today. And this is going to be vector fields that arise as gradients of functions. So let me just point out that a three-dimensional vector field is very similar to a two-dimensional vector field. A three-dimensional vector field, or a vector field on R3, is a function that assigns to each point x, y, z in some domain D in R3, a three-dimensional vector. And again, typically this is denoted with a capital F, but G, H are also used. Okay, and also we like to talk about this in terms of its component functions. So capital F of x, y, z typically is going to be the components P, Q, and R. Running out of room. Okay, so again, conceptually or pictorially, at every point in some domain in R3, you just draw a three-dimensional vector. And so this is really sort of truer to how we think about physics in 3 dimensions. So for example, if we look at the gravitational vector field that we saw in the last video, we can express this as a three-dimensional vector field. It's going to be very similar. It's going to be minus the gravitational field times the mass of the smaller body times the mass of the bigger body divided by the magnitude of x, y, z cubed times the vector x, y, z. And again, this just says that, let's say the bigger mass is the sum and the little mass is some planet or a spaceship or an asteroid or whatever. When it is at the position x, y, z, if the sun is at the origin and the little mass is at the position x, y, z, this is the force that is this represents the force that the big mass is exerting on the smaller mass. Now, of course, physically, they're both exerting forces on each other, but we just sort of think about the big mass as being stationary. Okay, so when we'll see how this ties into this definition in a moment. When capital F is a vector field, it could be a two-dimensional vector field or a three-dimensional vector field. But when capital F is a vector field, and there is a function, little f, I'll stipulate a real valued function, little f, such that big F, such that big F is equal to the gradient of little f. And again, this could be a real little f could be a real valued function of 2 or 3 variables. Okay, and there is a real valued function little f such that big F is equal to the gradient of little f. We say that big F is a conservative vector field. And we say that little f is a potential function for big F. So whenever big F is a vector field, it could be a two-dimensional vector field or a three-dimensional vector field, and there is a real valued little f such that big F is equal to the gradient of little f, we say that big F is a conservative vector field. So that's what we're defining, conservative vector field. And we say that F is a potential function for big F. Another thing we might say about little f is that it is an antiderivative of big F. and I will let you think about why I'm saying that. Okay, so to tie this in with the gravitational example, f of x, y, z, if this is the gravitational vector field, so this is minus the gravitational constant times little m times big M over the magnitude of x, y, z cubed times x, y, z. If this is true, this is actually the gradient of the following function. It's a gradient of this function. This is little m times big M times g divided by the square root of x squared plus y squared plus z squared. Okay, so the gravitational force field is a conservative vector field. And this right here, this function right here, is the potential function for the gravitational force field. And actually, this is called the Newtonian potential. Now, the reason it's called conservative vector field, we will see in the next section, but many, maybe, well, probably not all, but many fields from physics are conservative vector fields. And we will say what that means in the next section.